Throughout the world, coastal environments have been crucial venues for natural and cultural history. This video considers how to study coastal settings in the perspective of archaeology, toward appreciating how people have lived in these dynamic places through time. To a large extent, the dynamic aspects of a coast derive from the juncture of contrasting zones of land and water. Within these zones, numerous internal components can be discerned, and they each can interact with one another. These settings involve more diversity and dynamics than otherwise could occur in more homogeneous settings of singular biomes. Homogeneous biomes could be forests, grasslands, deserts, or other areas that overall could be described in singular terms. They always include some internal diversity, and they may be classified or subclassified in their terrain formations, water resources, and other aspects. Wherever two biomes meet or transition together, those transitions are known as ecotones. The transitional qualities of an ecotone can be variable, and they are notably complex in coastal environments. A coast could be regarded as an extreme version of an ecotone, and perhaps more effectively, a coast can be described as an edge zone. The edge in this case refers to the measurable line of two contrasting biomes, essentially formalizing the coastline as its own entity. Upon closer inspection in real life, the notion of a single coastline becomes impractical. With fluctuating tidal activity, the coastline constantly is moving. Even with measuring an average or mean tide level and coastline, these measurements can be variable during different weather conditions, lunar cycles, annual seasonal shifts, and longer timescales of changing climate and other circumstances. In the long-term views of archaeology and geology, coastlines always have been changing, constantly, and they will continue to change. If you can observe a tidal area through a sustained amount of time, then you can learn about the range of parameters of the tidal action and about what happens during each of those variable conditions. In particular, for archaeology studies, you can identify the processes for both deposition and erosion of sediments, tidal surge debris, and other materials that in total affect the formation of archaeological layers and remnants. Equally, you can recognize the habits of the local wildlife and other aspects of the natural setting that could influence the potential for people to live in these places or to use the various resources. Overall, tides bring materials onto the shore, deposited in elongated lines. During the highest tide events, this line of debris can remain intact and stranded until the next event of a high tide can reach to this landward point or higher. During strong stormy weather events, the low pressure in the atmosphere temporarily can cause the ocean level to rise, and these conditions can produce lines of storm surge debris. These lines of storm surge debris tend to be more massive and positioned farther landward than the ordinary high tide debris. At any beach setting, you should be able to identify what kinds of materials are being transported with the tidal activity. You can observe the matrix of deposits onto the beach, as well as the portions of those constituents that may be vulnerable to erosion and ongoing tidal movement. In the intertidal area, between the high and low tide marks, the repeated tidal action typically removes small and light material, while larger and heavier objects tend to remain on the beach surface, at least temporarily. During rising tides or stronger tidal activity, even the heaviest clasts and materials can be drawn back into the ocean. You can learn to identify the individual constituents of tidal debris as repeated events that undergo constant transformation, resulting in gradual accumulation of beach sedimentary units at a holistic scale. Generally, a beach surface will develop slowly and gradually, but the formation process can be punctuated by shifts in localized weather events or global climate. During exceptionally powerful storms and tidal surge events, some areas can be covered by massive debris, while others can be eroded or scoured. Patches of massive sand and detritus can be stranded in unusual positions, and they may or may not become vulnerable to the regular tidal action thereafter. Erosional cuts can remove large portions of sediments that otherwise had supported stable surfaces most of the time. Erosional depressions can cut downward in some tidal areas with a result of stranded low elevation spots that can fill with water, similar to ponds. Tidal surge events can reshape the character of a coastal environment. Most of the effects, though, may not be sustained through more than a few tidal cycles or seasons, and therefore the long-term condition of a coast will change slowly. Usually within timeframes of single years, regular tidal activity will bring a coastal setting back within the range of equilibrium inside its usual parameters. Generally, these parameters of equilibrium act at the scales of years or decades. The bounding parameters, however, could change through longer timescales of centuries or millennia. More rapid change can occur if numbers of high-energy tidal surge events follow one after the other without much time between them. Potentially, the effects of reshaping a coastal environment could be magnified by repeated high-energy events, especially if those events could be repeated quickly enough before the coast could return to its usual state of equilibrium. In any coastal environment, the most dynamic activity can be seen within the intertidal zone. The seaward side naturally delivers the most energy and activity from the ocean, while the landward side in itself remains stationary until it is affected by the wave action coming from the seaward side occasionally. Any coast includes an unstable seaward area within the zone of regular tidal activity, juxtaposed with a stable landward area outside the reach of most but not all tidal action. Slightly farther landward, the terrain can be even more stable, and it can support long-term vegetation growth and soil development. Meanwhile, the areas of tidal activity simply cannot remain stable long enough to support significant vegetation growth. Sometimes on stable surfaces, vegetation will start to grow, but then it will be eliminated by a storm surge event or another tidal action. In these cases, thin lines of organic debris and sediment can become buried beneath the later accumulations. These remnants of short-lived beach surfaces can be detected in fresh cut profiles, for example in spots of punctuated erosion, or inside artificial excavations. In these cases, the organic debris can be datable directly by radiocarbon, and the results can be invaluable for mapping the distribution of ancient beach surfaces during measured time intervals. In the intertidal areas, the unstable surfaces do not support vegetation growth, but they do attract shellfish and other animals. Often, birds come to these areas to search for food. Through time, the animals in a region can develop habits for certain times of the day, tidal cycles, and seasonal differences. Of course, the intertidal zone is not the only place of significance for animal life. Diverse plants and animals live in the stable landward terrain, as well as in the ocean itself. Only some of those plants and animals might affect the coastal zone directly, but all of these organisms contribute to the ecosystem in and around a coastal environment. In terms of terrain formations, plants, animals, and other factors, coastal settings involve more than a single coastline or measurable edge. Rather than a fine line between the contrasting entities of the ocean and a landmass, a coastal environment includes multiple habitats and micro-habitats over an extended space. These components together comprise a holistic coastal ecosystem that furthermore connects with the adjacent ocean on one side and a land mass on the other side. When interpreting coastal sites in archaeology, the context may be understood as involving the immediate vicinity of the coast as well as the adjacent habitats and resource areas. With this framing, you could evaluate how people in the past may have interacted with the different available habitats and niches for their living sites, for their food sources, and for other purposes. Often, coasts are situated with access to a diversity of natural resource habitats, including some within the immediate reach and others available at some distance. For research in archaeology, the most crucial natural resource is drinkable fresh water. In any terrain setting, water always will flow downslope toward sea level, and accordingly, water sources can be found along most coasts in variable forms. Most obviously, streams or rivers will drain downslope out to the coastline. In terrain formations without streams or rivers, the water table or aquifer floats above sea level, and accordingly, these sources could be accessed through natural caves, most easily in caves along the coast near sea level. Additionally, the water in the underground water table or aquifer can reach out to the coastline, where it can be found in natural seepage flows just above sea level and most safely accessed during low tide events. All of these possibilities are essential for understanding how people could have lived in and around coastal environments. If you can visualize the basic structural elements of a coastal environment in a general schematic sense, then you can identify those categories in their particularistic manifestations. Ideally, you can distinguish the contributing elements of a coastal environment in action today, as well as in the surviving ancient remnants. The basic principles of coastal formation have applied throughout the world's natural history and across the globe's diverse coasts. The results of the formation processes, however, have been different due to the variations in the shapes and qualities of the geological landforms in combination with the adjacent sea level. In any coastal setting, you always can observe the physical composition of the landmass as well as the angle of its slope where it meets with the ocean. The effects of tidal action are more severe in soft sedimentary units as compared with less impact in rocky exposures. The wave energy more easily can alter the shape of soft sediments rapidly and dramatically, while it can create slow erosion into solid rock formations. Limestone formations are especially informative in coastal studies. Originally, the limestone had been a living coral reef. After a change in sea level or tectonic uplift of the area, the coral reef was exposed above sea level. The coral then died and became solid limestone, preserving the overall flat, terrace-like shape of the former coral reef. Where the edges of the ancient reef now meet with the ocean, the limestone material eventually will be eroded by the ongoing tidal activity. The waves cut a notch into the limestone, and microorganisms may add more erosional effects. These tidal notches can be seen in action today, and numerous parallels are visible in ancient landforms. A tidal notch typically shows a parabolic shape. The parabola's deepest point represents the greatest amount of repeated tidal impact, for example within the range of the mean tide level that occurred most often throughout time. At the upper and lower ends of the parabola, the tidal impact was less pronounced, for example during the higher and lower tide events that overall were less numerous than the repeated mean tide events. In many places today, you can observe the surviving remnants of ancient tidal notches. In all of these cases, the relative level of the land versus the ocean has changed. This outcome could have occurred through tectonic uplift, as well as through lowering of the sea level. In some places, you may be able to coordinate an exposed tidal notch with other remnants of an ancient coastal environment. For example, you may be able to match the elevation of a tidal notch with exposed portions of an ancient coral reef, now visible as solid limestone. In these settings, you can reconstruct the former reef or paleo reef. Ideally, you can compare the paleo environment with the modern-day equivalents of sea level and components of the reef ecosystem. In Guam and the Mariana Islands, ancient coastal conditions can be reconstructed for the period of approximately 3000 through 1100 BC, when sea level was about 1.8 meters higher than the modern sea level. The measurements have been repeated in multiple instances, and the age has been confirmed by direct radiocarbon dating of the limestone and other associated materials. Moreover, these kinds of measurements have been consistent throughout the wider geographic region and even cross-regionally, pointing to a global condition of slightly higher sea level during this ancient time period. At a large scale of view, sea level globally has been rising for the last several thousands of years, following the last major ice age. Within this overall trend of thousands of years, however, some smaller fluctuations can be noted in the sea level history. Many of the world's ancient coastlines older than 10,000 BC have become submerged beneath the rising ocean. Nonetheless, other portions of ancient coasts have become exposed above sea level, depending on the time period in question. For instance, coastal sites of 3000 through 1100 BC can be found today in landward areas above the present-day sea level. In all cases, though, the localized geological uplift or subsidence may have created complicated outcomes. Coastal archaeology must account for the natural history of changing sea level in coordination with the possible vertical movement of an adjacent landmass. Even with approximate measurements lacking precision, you can be aware of how the coastal environment has changed through the last several thousands of years, and then you can develop a strategy for finding the ancient remnants of each relevant time period. Without this basic knowledge, you would not know where to look for ancient coastal sites of different ages. Often, these physical records from the past have become obscured or hidden in modern-day observations. Logically, looking only in the modern-day setting will exclude the opportunities to learn about the more distant past. As seen in Guam and the Mariana Islands, the ancient coastal conditions prior to 1100 BC involved a sea level slightly higher than the modern level. Accordingly, any possible archaeological sites of this ancient time period cannot be found on the modern coastal surfaces today. Many of the ancient tidal notches have been modified artificially with cup-shaped grinding basins that could not have existed prior to 1100 BC, and in fact most of these creations post-dated AD 1000. Likewise, many coastal caves could not have been accessible until more recently. The paleocoastal settings prior to 1100 BC involved substantially different conditions than can be witnessed today. Through knowing these basic parameters, excavations have confirmed that people indeed had been living in these islands prior to 1100 BC and at least as early as 1500 BC. The oldest sites here have revealed where people lived in houses raised on wooden posts close with the ancient shoreline. In these paleo-coastal settings, the ancient coral reefs contained lagoons with meadows of Halimeda algae. The bioclast of the Halimeda algae could shed within 1 or 2 years and drop to the lagoon floor, gradually accumulating as a thick bed of ancient bioclastic sand. Inside these ancient sedimentary units, the first inhabitants at these shores deposited their broken pottery, stone and shell tools, shell ornaments, food middens, and more. The ancient contexts of first settlement here at 1500 BC were transformed after 1100 BC due to the drawdown of the sea level from its temporarily higher level. Thereafter, the coastal environment continued to transform, eventually creating a new coral reef ecosystem and large coastal plain, as can be seen today. When approaching the modern-day coastal setting, numerous archaeological and historical sites are visible on or near the surface. This extensive evidence generally dates within the last 1,000 years in Guam and the Mariana Islands. Anything older would be undetectable on the basis of surface observations, and instead these older contexts could be known only through subsurface exploration. When exploring the subsurface layers, the findings would require careful documentation and interpretation. Without first comprehending how the coastal environment has changed through time, the sequence of sedimentary layers could be mischaracterized or misunderstood. In other regions, coastal archaeology has been more complicated. In the world's continental landmasses, the paleocoasts prior to 10,000 BC, for the most part, have become submerged beneath modern sea level. As a result, several millennia of coastal archaeology records have been missing from modern knowledge. For instance, the oldest sites in the American continents have been dated at least as old as 12,000 BC during the last ice age, yet the coastal environment of that period now mostly has been submerged under the ocean, except in a few unusual localized circumstances. Overall, the earliest coastal records in the American continents have been unclear, but the few known exceptions have indicated that, of course, people lived in these environments, migrated through them, and used these places in various ways. Due to the post-glacial flooding of the world's coastal landforms, the ancient Ice Age coastal sites and environments prior to 10,000 BC have been underrepresented and largely unknown in world archaeology. In some regions, coastal sites have been extremely rare until close to 5000 BC, when global sea level approached near the modern-day conditions. In other words, ancient coasts of the world have not yet been examined sufficiently for making confident conclusions about what happened there in the far distant past. Nonetheless, the given available clues all have pointed to the ability of coastal environments to provide diverse and reliable food, water, and other resources for groups of people. Coastal environments contain different habitats and microhabitats within close proximity of each other. In terms of potential cultural use, coasts can operate not only as resource zones, but also as corridors for transportation. Meanwhile, coasts offer opportunities for finding fresh water naturally near sea level. Additionally, protein foods of shellfish are accessible immediately at the intertidal zone on virtually a daily basis. Other foods of seaweeds, fish, birds, and other animals are accessible in the adjacent areas. At the landward side of a coast, the terrain can offer stable forest growth with suitable habitat for diverse foods and wildlife. All of these resources in their natural forms can sustain human populations, and potentially they could be enhanced or altered by people who can introduce different plants and animals, create new ecosystem dynamics, and generally transform the natural world. Realistically, coastal environments always have been influential throughout human evolutionary and cultural history, yet the archaeological evidence has been underrepresented overall. Most of the archaeological records from coastal sites have referred to the last few thousands of years, and sometimes only the last few hundreds of years close with modern conditions. The records of significantly older time periods will need considerably more exploratory research in coastal or paleocoastal archaeology. What are your thoughts about coastal environments as venues of dynamic natural and cultural history? What are the implications for learning more about what has occurred in these places in the past and what could yet occur there in the future? Thank you for watching here. I will see you in the next video.